Module 13, chapter 13 is about digital signatures. So now people can sign the documents digitally and they are acceptable in the court, and a lot of work is done nowadays basically with digital signatures. Okay. How many of you have signed anything digitally? Anybody has tried it? 1, 2, 3, 4, 5, 6, 7, half of the class. Okay, yeah. So basically, I use all the time, I don't know what document tool you use, but I use Adobe Acrobat. And the Acrobat has this nice signature thing. And so it does what we are going to talk about today. We'll talk about digital signatures, what they are, and then two schemes, actually three schemes, Elgamal, Schnorr, and the DSS standard. So what is a digital signature? Digital signature is that anybody can verify who signed it, what date they signed it, and what time they signed it, right? So they can verify that you signed it at this time and that you signed it. And you can authenticate the message contents and that the message has not been modified. So MAC is a part of the signature. If somebody can modify the document and not change the signature, then it is useless because you will say, well, I never saw this document. So this will not be able to separate the signature from the message. Can be verified by third parties to resolve dispute. And that's the other thing, is that anybody should be able to verify it, not just the recipient. So it cannot be based upon secret keys. So the way it works is that you take the message M and you run it through an algorithm for digital signature using your private key. So this requires private and public keys. This requires a public key system. So you use your private key and then you get a signature. You put that signature with the document and you send it to the other side. The other side can use your public key to verify that you signed it, or if nothing else, they will just file it in a drawer or on a disk. And 3 years later, when there is a dispute, they can take it to the court and say, look, 3 years ago, this person signed it. So there is a time, date, and the content, and the signature, everything else. And using the public key, anybody can verify that, yeah, you must have signed it because you are the only one who has the private key. Right? So this provides for the source non-repudiation. Source cannot retract and say, well, I didn't sign it. Okay? So the same thing is said here again, I think, is basically you take the message, hash it, and then you can encrypt it if you want to, encrypt the whole thing message. Oh, well, what they are saying is that you can hash it and you can encrypt the hash using your private key. So that will become your signature. Basically, because if somebody changes the message, the hash will change and then it will not match the signature. So instead of doing cryptographic hash, now this can be a secret key or it can be without the key even. So this is a cryptographic hash. So MD5 is a cryptographic hash without a key. SHA-1 is a cryptographic hash without a key. You could do any of those hash functions. And so anybody can get that tag, that hash. You encrypt it with your private key and that becomes your signature. On the other side, the message comes, the other person can do the same hash and then they can do that and they can decrypt your signature and compare the two. And if they match, then we know that it was you. So the signatures will have lots of attacks, and this is how the attacks are named, are classified. Where C is the attacker and A is the victim. C is the criminal, A is the victim, right? So one attack is key only attack. So what can you do if you only know somebody's public key? That's a lot of work. If you just know public key, to find out the private key and then to be able to break the signature, modify the message is a lot of work. So that is very difficult. Then known message attack. That C has a set of messages and signatures. So you are signing many documents. Somebody could collect all those documents. So now they have many samples that they can analyze. So they will have easier time trying to figure out your private key. Chosen message attack is that he can get your signature on any document that they like. Then they will have even more easier time. It's not that whatever you have signed, it's whatever they want you to sign. Right? So that will be even easier. And then directed chosen message attack. So A's signature on messages selected after knowing A's public key. So C selects, so very selective messages they send. And then adaptive chosen attack, where they look at your signature and they say, okay, I need this more bit. So they send you another message, which really helps them find that bit. And then they send you another message. So that is they analyze and send, analyze and send. So these are more and more directed. So this is generic chosen, this is directed chosen, this is adaptive chosen. Is that basically they can collect signatures, and the more signatures and more classified signatures or more directed signatures they can collect, the easier it is for them to attack you. So the key-only attack is very rare and very difficult. Then forgery, crime, total break. C knows A's private key. If somebody breaks into your computer and gets your private key, that's a forgery, right? That is possible. Universal forgery. C can generate A's signature on any message. So this is a crime which basically C will have to know your private key to be signed on any message, but there could be some way so that, and I don't know how that is, but basically there could be some way so that without knowing the full private key, the C could still generate signatures. If you had a very big signature algorithm, which I don't think is possible. So anyway, so this is a universal forgery. Selective forgery is that C can sign only some documents. C can generate A's signature for a particular message chosen by C. So they have some idea of how to find signature for this message. Okay. And then existential forgery can generate A's signature for a message not chosen by C. And so that is going into the other direction, which is universal direction. They can sign any message, but they can sign some messages which they didn't choose themselves. So these are just method of classifying the crimes, not really much more than that. But so we are going to talk about three schemes, starting with the Al-Gamal. But all these three schemes have this requirement. First is that the signature must depend upon the message signed. So there is no such thing as universal stamp. Like we used to do before, signature was just something handwritten and everybody could copy that and paste it on something else. So it has to be very specific to the document. Right? So if you change the document or you do anything with the message, the signature is not valid. Must use the information unique to the sender, and also it must be unique to the sender. So basically, so that there cannot be any forgery or denial. Must be relatively easy to produce. So that's another thing, is that the signatures cannot take too much time, and so they have to be easy to produce. So like we saw in this algorithm here, cryptographic hash, we didn't want to use the whole message and run it through the private key. That would be a lot of work. So we just run the hash with the private key. So that is for this purpose. It's easy to produce. Must be easy to recognize and verify. Same thing. When somebody gets it, they can verify it and they can recognize it who signed it. So when you sign it with Adobe Acrobat, you see they put your name, which is readable, and they also put something which looks like a signature, just so that it feels like a signature. So some handwritten stuff. and then they have something behind it which you cannot see, which is really the digital signature. Okay, so anybody can recognize it, anybody can verify it. Be computationally infeasible to forge. So while it is easy to produce, is it very difficult to forge. Either on the new messages or for a given message. Okay. Be able to retain a copy of the signature in storage. And second thing is these signatures will be stored for a lot of years. So this will be valid for the length of the document or life of the document. By the way, on many of these slides, I put Wikipedia references. And the reason is that I think there is more information there which is in addition to what is in the book. So I would recommend that you read those URLs, click on those URLs and read them on Wikipedia, or you can just go to Wikipedia and say electronic signature. And so there is additional information, additional to what is in the book. Not every slide has it, but some slides have it because there is extra information. All right. So we talk about the first scheme, El-Gamal digital signature. So this is the same guy who did the encryption. Now we can use something similar for signatures. And we are going to see three schemes. And all three schemes, basically what happens is that you send something with the document, which we call signature, which is a function of that function that can be verified. So every signature scheme has a particular function. So we will see what function this El-Gamal uses. What he does is he takes the hash of the message. So you take message M and get the hash. And then you choose a random number K between 0 and Q minus 1. This hash is between 0 and Q minus 1. Okay. So we skip this slide, sorry. Signature variant of El-Gamal, I think I already said that. And then each user generates his or her key with the private key which is selected between 1 and Q minus 1, and then the public key which is given out. Okay, so maybe I should repeat this part, yeah. So first of all, we select a very large prime Q. And we know its primitive root alpha. Q and alpha. Okay. What is the primitive root alpha means? Anybody remembers what is the primitive root? What does primitive root do? Good. Yeah. If you do a square, a cube, a raised to q minus 1, you will get everything from 1 through q minus 1. So that is the primitive root. And so you select one number xa, which is your private key, and then you raise a raised to xa, that is your public key. Okay? A raised to xa is your public key. So everybody knows this, but they can't find out x. They cannot find out xa. That's the whole difficulty. So all right. So we have M, which is the hash, and then we select a K, which is a per message key. So now K is different than XA. K is per message key. For every message that you want to sign, you select a different random number, and then such that GCD K comma Q minus 1 is 1, so that K is relatively prime to Q minus 1. Then you compute S1, which is A raised to K mod Q. All right. S1 has nothing to do with the message so far. Then you compute K inverse, which is inverse of K mod Q minus 1. And then you compute S2. This has to do with the message because S2 is equal to K inverse times M minus XA times S1. All right. M is the hash. XA is your private key. S1 is this number that you had already computed. And then you multiply it by K inverse and you do the mod Q minus 1. This is basically this signature. Signature is S1 and S2. You have to send both. So basically, if S2 is 0, if S2 turns out to be 0, then you have to start from the beginning again. You get a new K, another K, and then you get that. Okay, you don't want to have a 0 because that is very easy to break. If you send somebody S1 comma 0, they can easily break it. So we don't want to do that. So we send S1 and S2, these two numbers, and that is the signature. S1 basically is like a public key for the message. Right? This is the key we selected, A raised to K. If I would have put XA there, that would have been my public key. But this is the message's public key. And again, they cannot calculate K from S1, so we just send them S1 and S2. Now, anybody can verify that, and actually I will continue on this slide next time by doing these two operations, V1 and V2, and if V1 is equal to V2, then clearly all of these things are valid. So we will do this math next time.